the fundamental theorem of line integrals. Remember that the fundamental theorem of calculus says the definite integral of f prime of x while x is bounded between a and b can be written as f of b minus f of a. And f prime is continuous function on closed interval a and b. Now we're going to generalize the idea. We're going to introduce this theorem that's saying that now suppose C is a smooth curve given by the vector function r of t, where t is bounded between a and b. So you have this given interval. Let f be a differentiable function of 2 or 3 variables whose gradient vector, which is denoted by nabla f, is continuous on C. And again, C is a smooth curve given by a vector function r of t. With this given information, we can generalize the fundamental theorem of calculus and say that, hey, the integral over curve C of nabla f or gradient of f, which intuitively can be assumed as the derivative of the function, dot product with dr, which is the differential of this vector, is equal to, instead of f of b, now you have f of r of b, the terminal point, minus, now for f of a, you're going to use f of r of a. So this is what we have. This is what we are introducing, generalizing the fundamental theorem of calculus. Now that we defined this and we introduced the theorem, we're going to introduce another theorem. If the integral of f dot dr over smooth curve C is independent of path in D, it means that the integral of f dot dr over curve C is equal to 0. So wherever the integral of f dot dr over smooth curve C is equal to 0, for sure you can say that, hey, this line integral is independent of path. And please note that C is a smooth curve and it is closed path. For example, you can visualize C this way. Starting from the initial point, going to the terminal point, it is closed. Also, another theorem for you. Suppose F is a vector field that is continuous on an open connected region like D. If the line integral of f dot dr over curve C is independent of path in D, then F is conservative vector field on D. It means that you can find the potential function F such that the gradient of F is equal to F itself. 3 important theorems for you. In this example, we want to find the work done by the conservative field, which is given to you as yz in the direction of x-axis, plus xz in the direction of y-axis, plus xy in the direction of z-axis. We can easily see that this is basically the gradient of the multiplication of x, y, and z. If you take the partial derivative with respect to x, you get yz. If you take the partial derivative with respect to y, you get xz. And if you get the partial derivative with respect to z, you get xy back. Well, you want to calculate the work done by this field along any smooth curve C joining the point A, -1, 3, and 9, the second point B, 1, 6, and -4. Okay, let us begin. Since the potential function is x, y, and z, we have the integral f dot dr from A to B, which by definition is the integral of wherever you see f, we're going to use the gradient of the potential function dot dr. Now, remember that f is equal to the gradient of f, and it is equal to, this integral is equal to f of b minus f of a. We're basically going back to the formula that we presented in this theorem. If the integral is independent of path from a to b, its value is f of b minus f of a, and f is basically the potential function. Perfect. So this is basically the potential function x, y, z at the terminal point, which is 1, 6, negative 4, minus the potential function x, y, z at the initial point, which is negative 1, 3, and 9. All you need to do is do the substitution. You have 1 times 6 times negative 4 minus negative 1 times 3 times 9. If you do the calculation, the work done is positive 3. So the use of the line integral f dot dr is basically calculating the work done by conservative vector field.